Hello, everyone. Good day. And my name is OLADIPO FATUKASI. I'll be sharing with you on evaluating the unknown, the fundamentals of formation evaluation. I want to thank Earth, Energy, and Environment Student Conference and Exhibition hosted at Marietta College for the opportunity to share from my experience on this particular topic. Here's my outline. What is formation evaluation? An overview which contains a problem statement. And what is formation evaluation? Why do we do formation evaluation? What data are we interested in? Who needs this data? What tools and methodology? And then the summary and a brief, quick look evaluation exercise. Okay, there is a challenge, and it's a global challenge. It's the growing demand for energy in every nation across the world, whether you source it from oil, gas, coal, or renewables. There is a growing demand for energy, and research has found that the worldwide demand will continually rise steadily, even beyond 2040. But specifically for oil and gas, projected demand by 2040 is 45% more than it was in 2014. And that would mean 1.5% increase per year. And this is just one of the growing concerns, of course, alongside campaigns for cleaner energy, use of renewables to replace fossil fuels, which has contributed to emissions that have depleted the ozone layer, which has given rise to increased sea levels, drought in many countries, wildfires in many countries, and even flooding as well. So these are challenges that we are facing as an energy industry, but specifically as an oil and gas industry, we have our own challenge as well, in line with the global challenge, which is ability to meet up with the global demand for energy. Now, statistics has it that if production continues from existing fields alone currently, that by 2040 would be left with about 40 million barrels of oil per day and even less across the world, which is not going to give, or which is not going to support the global demand of about over 200 million barrels of energy of oil, or million barrels of energy that will be required in the year 2040. Our challenge now is increasing production, basically with more environmentally responsible ways, more cleaner technology, and this has contributed to our own challenge as an industry. And what's the way forward? We need to explore for new fields that we don't know yet exist, like was recently discovered in in the United States of America, right? And even discovering many in Africa today, in today's world. Angola, Nigeria are discovering new fields, exploring static fields, that is hydrocarbon fields that we know about but hasn't been produced economically, and even going as far as confirming probable fields that we suspect that there's hydrocarbon here, and then we need to conduct more drilling for confirmation wells to know if indeed there's hydrocarbon here and how much hydrocarbon is there. And this is the part where formation evaluation really comes into play, because we do not want to discover hydrocarbon in an area that will not be economic, right? And this is why formation evaluation is very important. So this is also just buttressing global demands challenge. And let's go into formation evaluation proper. What is formation evaluation? Formation evaluation is simply the application of scientific principles, engineering concepts, and technological innovations in the exploration and prospecting of hydrocarbon resources in geological formations in an environmentally sustainable and responsible manner. Formation evaluation is also the process of interpreting a combination of measurement taken inside a wellbore to detect and to quantify for oil and gas or hydrocarbon reserve in the rock adjacent to the well. And professionals who are saddled with the responsibility to evaluate formations or to evaluate hydrocarbon in the formation are called petrophysicists. So what is formation evaluation? This is I put together 5 questions that I love to ask myself as a student, and I believe that they guide literally for every petrophysicist that is out there around the world. So formation evaluation, these are the 5 legs or 5 questions that must be answered to really indeed evaluate the formation. Number 1 is there hydrocarbon here at all? Number 2, how much of hydrocarbon do we have here? Number 3, how much can we produce? Number 4, at what depth are they located? And number 5, very important, how much money can we make from this particular discovery? So geological data and their scale. This is just showing us from a mega scale to a fine scale kind of data that we can use in formation evaluation, from the regional analysis, understanding regional analysis, to basin analysis, to block analysis, to prospect analysis, to field analysis, and to compartment analysis. And from this understanding of the scale of geological data, we can get 2 kinds of data or 2 kinds of geologic measurements: surface measurements and subsurface measurements. So what are surface measurements? These are measurements that we can see with our eyes, and we can measure with tools that with our hands or with machines. And some of the surface measurement that we can observe are topographic maps, surface geology, which would include structure and stratigraphy, nearby outcrops, heat flow measurements, hydrocarbon seepage, and so on. And then for the subsurface measurement, we have data directly from the well, which can either be direct or indirect. Now, your direct measurements from the wells, of course, the wells are below the surface of the earth. The direct measurements are samples that we can collect, and the indirect measurements are basically measurement that we can't collect, but we can measure with the aid of sensors and other technological materials. So direct measurements contains samples such as our cores, our mud logging or our mud, also contains our cuttings, our ditch cuttings. And then for indirect measurements, talk about our seismic 2D, 3D, 4D logging, talk about gravity, magnetics, and so on. In fact, under our logging, we can also get vertical seismic profile, VSP, which is very useful for seismologists, as it were. So let's talk about these samples or these different subsurface measurement that we can derive. So for the direct, we have conventional cores. Now, our best data comes from conventional cores. It shows, at the depth of interest, we will stop drilling, and then a core barrel or a core gun is pushed into the rock at the base of the hole, and then the sediment or the core is retrieved. And this picture here shows us three different kinds of, or 3 different examples of cores. We find that this is very coarse, showing that well, probably gravel or pebbles. Find this finer, well sorted sand, and then we find these alternating sand and silt in this core. Now, conventional cores can give us information concerning our reservoir, our source, and even our seal. For reservoir, it tell us about the lithology. It tell us, of course, from this you see that silt and sand alternating over here. So lithology is clearly seen with conventional cores. It helps us with grain size and sorting, sedimentary structures, ripples. We find a lot of structures on our cores that would, in fact, can also indicate presence of microfossils. Environment of deposition for our soils can indicate organic richness, organic quality, thermal maturity, and for seal, layering, vertical permeability, age of fossils, and so much more that our conventional cores can do for us. from our ditch cuttings. Our cuttings basically, I mean, as an analogy, it's for instance, when you want to drill through a wood and you begin to drill, you find out that wood shavings begin to come to the surface. So it's the same thing, same way when we are drilling through a formation, mud circulation in the hole pushes or lifts the cuttings right back to the surface. In it could be in a different, it could be in different styles that could be done, but that's not the topic for today. So let me just mention that our cuttings are very important. Of course, they are cheap to get. They're also very quick to analyze, and they give indication of lithology and even the age. But the problem that we encounter with ditch cuttings is that the rock sometimes are pulverized, are crushed, so we cannot get exact properties or precise properties that we need from these ditch cuttings. Again, we cannot ascertain. Sometimes there's a disparity between the depth at which that cutting comes from and the time it travels to the surface of the earth where it's collected and then analyzed. So let's go to the indirect, which is also a kind of subsurface measurement, but this time around deals with more technology, such as the well log. Now, the well log is a record of one or more physical measurements as a function of depth in a borehole. In this image, you find a thread of wires, and then you also find a compartment behind, which is a receiving or processing room. And what this does is a sensor is basically attached to this thread of wires, and then is let down into the hole, and at different intervals it sends back information to this receiving room where a professional is there to analyze the different kind of data that is gotten from the different kind of sensors. We can have the gamma ray, resistivity, the neutron density. We can have the caliper, the sonic, different kinds, and we're going to see that as we move as we continue in this presentation. So these are common logs and what we use them for. We have logs such as lithology. We have logs such as, I beg your pardon, gamma ray, spontaneous potential, sonic density, neutron resistivity, nuclear magnetic resonance, photoelectric effects, wireline testing, well test, deep meter, including bow imaging, and then core. And then these are properties that we can derive from these logs. We can derive lithology, porosity, fluid type, can derive fluid saturation, we can derive stratigraphy, downward pressure using wireline testing and well test. We can also derive geophysical properties using sonic density logs. The ones in red are showing the primary use of the logs. That is what we use these logs for primarily. So for lithology, we use gamma rays, spontaneous, and of course the core. For porosity, we use sonic density, neutron, and core majorly. For permeability, we use majorly the nuclear magnetic resonance. We use well testing, we use well test, we use core for permeability. And then for secondary use, we can infer from resistivity, neutron density, sonic, and even spontaneous potential. So what do this log measure? I've mentioned earlier, I've given you lithology, porosity, fluid saturation, permeability, acoustic velocity, density, and so much. When these are examples of sensors that is attached or that are attached to the wire lines and that are lowered into the hole. But let's look at an overview of 5 key logs that are used in formation evaluation. The first, caliper log, which measures borehole size. The second, lithology logs, which measures lithology, as the name implies. That is, it could be sand, it could be shale, it could be limestone, it could be dolomite. Third, we have porosity logs, which measures porosity and fluid types. And 4, velocity logs, which relates well to seismic data. And number 5, we have resistivity logs, which basically measures conductivity, or as the name implies, resistivity, which identifies or indicates or infers hydrocarbon bearing zones. So caliper logs, what do they measure? The diagram to our right shows us an example of a caliper log with 3 arms. And what happens is that these arms are pushed out hydraulically, and they touch the side of the borehole. And the hydraulic system, which are calibrated in inches or centimeters, will give information to correct the log for sensitivity to bore sides. It can also be used to determine how much cement is used or will be needed when casing, what kind of cement as well, when casing or lining the well. And it can also be used to, obtain certain lithologic information where areas of washouts, areas of loose or unconsolidated rocks, also to determine stress fields from borehole breakouts. And then we have lithology logs. Two kinds of lithology logs, basically gamma ray and the spontaneous potential. Now, the gamma ray basically measures the amount of naturally occurring radioactive elements such as uranium, thorium, potassium present in a lithology. Now, when we take a gamma ray reading, when the sensor is moved or is lowered into the well and it encounters a lithology such as shale, which has a very high propensity to contain naturally occurring radioactive elements, the sensor sends back information to the receiver and it reads a very high gamma ray reading. Let's take, for example, we have a scale of 0 to 100, just like we have here, and we have a baseline at 50 to just divide the scale to show us the point where it crosses over to being a very high gamma reading, which will indicate shale, and then a low reading, which will indicate sand. So when it passes through a lithology that contains sand, which cannot contain so much of radioactive elements, it will read low. It will read low, and that indicates, just shows us how important it is in helping us differentiate lithologies. The same for spontaneous potential, which basically just measures potential difference between the voltage in the well bore and the voltage or the electrode at the surface. The electrode at the surface. So basically, it works the same as gamma ray. If it deflects to the right, it indicates shale. If it deflects to the left, it indicates sand. Porosity logs. Porosity logs are divided into two, and these are very important logs: density, porosity, neutron porosity. Density porosity is what we have as RHOB on the diagram to the right, dotted, with a red line, and then neutron porosity is the blue dotted line that we can find. And what the density porosity measure basically is the average bulk density of the formation. It could be the average bulk density of the rock or the average bulk density of the fluid present in the rock. Now, the neutron porosity measures the hydrogen concentration and hydrogen ion concentration present in that formation for both logs. For both logs, deflection to the left would indicate more porosity, and deflection to the right will indicate less porosity. But more contextually, we find out that the logs arranged over each other, that is the density and the neutron porosity arranged over each other. But for the density, we find a scale increasing positively. And then for neutron, we find a scale reducing. So we have from 0.45 to minus 0.15. What is interesting about this log is even as they are inverted on the scale, whenever we find a cross inversion, that is, whenever we find density reading high and neutron reading high, that is when density tends to the left, when density tends to the right, I beg your pardon, for the one in red, and when neutron crosses over to the left, neutron is the one in blue, we have an area of interest. It indicates something interesting for us as petrophysicists whenever we are carrying out formation evaluation. Now, our sonic log, basically it measures the time it takes for sound to travel a specific distance. The measure of this interval transit time is what we refer to as delta T, and it's measured in microseconds per feet or microseconds per foot. It's very important for seismologists because this is the principle by which seismology works with, which is basically travel time from a receiver when it intercepts a structure, and then time is sound is reflected back to the surface. So that travel time is what is measured and what is used to then derive what we call our seismic data, which is very important and very accurate representation of the subsurface. And very key for seismology. So we also have a log for that, and we can use that to now juxtapose what the seismologists must have gotten from sounding, from doing their own, from carrying out their own sound analysis of the land or of the subsurface. Resistivity logs. Resistivity logs basically measures electrical resistivity of the formation or electrical conductivity of the formation, and the device or the tools these tools are designed to investigate the different distances into the rock. For instance, I put here that the resistivity logs can either be deep, medium, or shallow, depending on how far into the formation resistivity wants to read. So for deep resistivity, we can have a more precise or more accurate values for, and if it reads high, it will indicate hydrocarbon bearing, because hydrocarbon is very resistive to electricity. And if it reads low, it will mean that we have shale, which is very conductive to electricity. This is a workflow that I used in a petrophysical evaluation of a field onshore Niger Delta in Nigeria, and I used TechLog for that. But these are other software that we can use. We can use Petrel, we can use TechLog, we can use Geolog, we can use interactive petrophysics IP whenever we are conducting a formation evaluation. So who needs what? Who needs what? What the information we get from formation evaluation, who needs them aside the aside the petrophysicists, because formation evaluation is very important, as is a core operation in the oil and gas sector. And without the data accurately evaluated, there cannot be production, because no company has money to throw around into the air. So for the geophysicists, they will need the time to depth relationship for their seismic profiling. For the geologists, they will need stratigraphic information, structural sedimentary features, mineralogy, bedding planes. Reservoir engineers will use porosity, permeability, fluid contact, even down to the manager who uses the hydrocarbon, the value, exact figure of the hydrocarbon in place, which is what we want to do, which is what we want to derive as petrophysicists. The recoverability, cost of development, profitability. The government also needs to take record of all the data that we used, our FDP, which is our field development plan, and of course, profitability for national economy. I put here a quick look evaluation that this is a real-time data using TechLog, of course, of the same field, onshore Niger Delta in Nigeria. Unfortunately, I can't display that on the software because of confidentiality rights of the company that supply the data, but I can share this picture. And you see, the part I highlighted here is what I call the zone of interest. So remember, as I've shared with you, that from our gamma ray reading, it helps us to tell what lithology we are in, and it has helped us by separating the regions of high gamma ray reading, which contains high radioactive elements, from the low gamma ray reading, which contains the regions of low radioactive elements. The areas of high radioactive elements are our shale, and low is our sand. And our sand basically is our reservoir in the Niger Delta. And so if it's a sand, it will resist electricity more. So we find here again that electricity reads very high compared to the shale region, which resistivity reads very low. So resistivity reads very high in the sand region, and of course in the maybe I can zoom this a little bit. I can zoom a little bit for us so we can see. So we see that neutron density, we find out that the red moves towards 1.9, and then our neutron moves towards -15, and then which is not what we find in this area of shale, gives us this little separation, which is very interesting for us, that can be an indication for oil. And here as well, we find that the volume of shale, which is another kind of log that we can get that would help us, that would tell us exactly how much shale we have present in that region. We find that volume of shale in this highlighted region is very low. We also find out that the hydrocarbon saturation is very high and water saturation is very low, which can be a very good indication that we have oil and gas or hydrocarbon reservoir present here. So another example would be what we have here. So we find out that resistivity is very high in this region. We also find out that neutron density also crossed, and we find a low neutron reading, a very high density reading, which is good for us. A very low volume of shale reading, a very high a very high hydrocarbon saturation reading, which is as well very good for us. So this zone can be an area of interest for us as petrophysicists whenever we're doing our formation evaluation. This is another example. Interesting. You can see a sand and high resistivity compared to this shale, So good. You can find a low volume of shale here and very nice distinction in the hydrocarbon saturation. So this is also an area of interest. Thank you very much for listening. Once again, I want to thank the Earth, Energy and Environment Student Conference and Exhibition for the opportunity. Thank you very much.